Hello, this video is about steel slag. It will cover the different forms of steel slag, how they are produced, how they are added to a cement mixture, and their effects on the mixture as well as the concrete. So what is steel slag? Steel slag is a byproduct of steel production. It occurs during the separation of molten steel from its impurities. There are many grades of steel that will greatly alter the type of slag produced. Grades of steel can be classified as high, medium, and low, depending on the carbon content, where highly graded steel will have a high carbon content. This requires higher oxygen levels and increased levels of lime and flux for the removal of impurities. This will result in elevated levels of slag produced for the use in cement applications. Steel is manufactured in a process comprised of several phases. These phases involve the reduction of iron ore into pig iron, followed by the refinement of the iron into steel. It is then later formed into different shapes and compositions for distribution. During the first steps, iron ore exists in its molten phase at about 1500 degrees Celsius within a blast furnace. At this moment, the impurities bind with oxygen and mix with the added flux to form a layer on top of the iron, where it would normally be removed and treated as a waste material. However, for use as a cementitious material, it will be decanted, meaning it is separated into a different container. This is where it will be rapidly cooled to a temperature below 800 degrees Celsius to keep certain materials from crystallizing. It is then crushed into a sand-like material to be added into the cement. This sand-like material is referred to as ground granulated blast furnace slag. This figure shows a basic oxygen furnace, where hot metal, scraps, and flux will be added. High heat and high pressure oxygen is then injected into the mixture, where it will chemically bind with the impurities and create slag. The addition of flux lowers the viscosity of the slag and prevents oxide from forming on the surface of the molten steel, creating a distinct layer. Steel slag is often used as a partial replacement of fine and coarse aggregates in cement. Aggregates make up approximately 70% of the concrete volume and can be costly when it comes to the incorporation of natural sand. This started the search for alternative materials. Steel slag is one of the most common industrial wastes, which makes it a popular cost-friendly substitute in most structural cements. As the amount of steel slag incorporated into cement increases, the mechanical properties of the cement will also change drastically. One of the cement properties that needs to be considered is the workability. This will change the application of the cement and its curing process. The workability can be monitored by performing a slump test for different ratios of slag used. The compressive strength of concrete will gradually increase with the addition of steel slag until it reaches around 30% replacement for coarse aggregates and 40% for fines. After this point, compressive strength will decrease. Many other changes to the mechanical properties will occur to the structural cement with the addition of slag. This will be investigated in further slides. Since steel slag is produced as a byproduct in the steel production, it has a varying chemical composition, but can be approximated as about 45 to 60% calcium oxide, 10 to 15% silicon dioxide, 1 to 5% aluminum oxide, 3 to 9% iron 3 oxide, 70 to 20% iron 2 oxide, and 3 to 13% magnesium oxide. Steel slag also has various mechanical properties in each of its applications with cementitious materials. Steel slag used as fine and coarse aggregates at certain percentages in cement mixture can increase the overall compressive, tensile, and flexural strength. Steel slag aggregate can also increase the resistance to acidic exposure. However, it can reduce the workability of the concrete. Steel slag applied in cement clinker does not significantly affect the concrete specimen, however, does have a slight decrease in strength. This graph compares the compressive strength of slag cement mortars versus time cured. It can be seen that at the earliest stage, the compressive strength is fairly low, at 21 megapascals. But at 100 days cured, the mortar yielded a compressive strength of about 65 megapascals, higher than regular Portland cement concrete. There are various applications for steel slag cement. Each depend on the specific slag and mechanical properties. Some uses include highway construction or structural applications. Slag cement can be used widely in residential concrete applications, which is becoming increasingly more popular for aesthetic reasons. Steel slag cement is used for footings, sidewalks, driveways, and even some structural uses in the houses themselves. The reason for incorporating slag into these cement mixtures is to lower the cost and increase energy efficiency. Precast and pre-stressed concrete can utilize the benefits of increased early strength when steel slag is incorporated into the cement. Heat curing is often used for the production of precast and pre-stressed concrete, as steel slag responds well to heat curing and produces higher strengths than traditional Portland cement concrete. Slag cement in high-performance concrete has an increased compressive and flexural strength, lower permeability in heat generation, and a greater resistance to alkali silica and sulfate attacks. This is the Reliance Stadium in Houston, built with high-performance concrete created with steel slag cement, creating 4 super columns that support the retractable roof. There are many standards and classifications created by the Canadian Standards Association as well as the American Society for Testing and Materials for different cement mixtures. A specific example pertaining to the compressive strength of cement with the addition of ground granulated blast furnace slag is ASTM C989. This states different grades of a slag cement mixture based on its compressive strength of a mortar cube compared to that same mixture in the absence of slag. The slag activity index is calculated to place the mixture into said grades, calculated as the compressive strength of the slag cement mortar divided by the compressive strength of the mixture without slag. It can be noted that in the table, at 7 days curing time, the slag activity index is less than 100, meaning that the cube without slag was stronger, though at 28 days for grade 120, the index became greater than 100. This is because the addition of slag slows down the hydration of cement, but results in an overall higher compressive strength at a longer time cured. This is a test report from a company called Heidelberg Cement Group. It includes the standard chemical and physical requirements, the slag activity index, the reference cement properties, and the compressive strength of the cement mixtures in accordance to ASTM 989-05. In the standard chemical and physical requirements row, it shows certain chemical amounts within the sample in percent weight and the maximum allowable as per ASTM specifications. Additionally, certain physical properties such as the density and the air content were measured and compared to the standards. All of these requirements are met. The slag activity index, explained earlier, is found in the second row. It is seen under the test results column that the slag activity index is above 100, meaning this particular sample has a higher compressive strength with the addition of slag and is above the minimum requirements for both grade 100 and grade 120. The reference cement row shows the composition of the cement being tested. The final row shows the compressive strength at both 7 and 28 days for both the reference cement and the reference cement with the addition of slag. It can be deduced from this section that the addition of slag results in a higher compressive strength. Steel slag has many applications in the production of cement, each application with its own benefits. Steel slag is an energy-efficient substitute for cement clinker. Production of clinker demands large amounts of energy and in response produces a large amount of CO2 emissions. Substituting clinker for steel slag will significantly decrease the amount of clinker needed to be produced. Steel slag cement has beneficial mechanical properties as well, including increasing the overall compressive strength, resistant to chemical exposure, and resistant to alkali aggregate reactions and salt corrosion. In short, steel slag is a byproduct of steel production that would otherwise be treated as a waste material without its incorporation into steel slag cement. It can be used easily as a partial replacement for fine and coarse aggregates, as well as for clinker, depending on the specific kind of slag produced. Slag greatly improves mechanical properties and creates a wide variety of infrastructure projects. Due to the fact that slag is considered a waste product, utilizing it in other applications reduces the impact on the environment significantly, as well as reducing the cost for cement production.